Segment 8 begins with more conversions using our ever-growing toolbox of conversion factors. We have Avogadro's number, we have molar mass, earlier we had density, we had foot to inches, yards to feet, feet to miles, etc., etc., etc. So you should be thinking of your conversion factors as being something like a toolbox. You have to get the right tool for the job. So on the bottom of page 12, our starting place, our ending place, moles of aluminum oxide to atoms of aluminum. Our plan is that we need to go from mole Al2O3 to moles of aluminum to atoms of aluminum. 1 mole Al2O3, 2 moles of aluminum. That's an interpretation of a definition. That's our conversion factor. 1 mole of aluminum, 6.02 times 10 to the 23rd atoms of aluminum will then give us 3.9 times 2 times 6.02, 7.04 times 10 to the 24. So let me try that again. 3.9 times 2 times 6.02, 3.9 times 2 times 6.02. I have a new calculator. 4.7 times 10 to the 24th. 4.7 times 10 to the 24th. That should be our answer there. So you guys double check. On this one, grams to mole means we don't need a mole ratio. We don't need Avogadro's number. We don't need all these other tools. The tool from our toolbox is simply molar mass. Our molar mass is 14 plus 2 times 16, 46.0 to the 10th place. 46.0 goes in the denominator. And we simply divide. 138 divided by 46 is 3. 138 divided by 46 is 3. So I've tried that twice. Okay. 2 3 significant figures is 3.00 moles. Okay, so as always, pause, practice, keep working on these. Okay, so now we're going to talk about how to put this into the chemical equation. So this would be like cooking. We have our bag of groceries, and now we want to cook. We actually have to follow a recipe. And this should not be new either. Okay, so if it's helpful for you, pause, watch your ancillary videos, go to your book. However this works for you, okay? You have to practice just like cooking, okay? Now, if we have stoichiometric coefficients, it shouldn't be a stretch to say that if we take those coefficients and put them into some sort of recipe, that we're going to call that stoichiometry. So I like to start with something familiar. So let's make brownies. Okay, so we have our brownie recipe, and our recipe should be familiar. 1 mix, 3 eggs, 1/4 cup of oil, 1/4 cup of water, heat it up in the oven, and we get our pan of brownies. Okay, how many eggs will it take to use up 4 mixes? Well, don't forget your process. Your starting place is 4 mixes. Your ending place is eggs. So you need to know what the relationship is between mixes and eggs, and that's where we get it from the recipe. 1 mix to 3 eggs. That's our mole ratio. 1 mix, 3 eggs. Mixes will cancel. 12 eggs, and we're going to ignore our significant figures rules because it doesn't make sense for us to say 10 eggs, okay? How much water will it take to use up 1.5 cups of oil? Okay, 1.5 cups of oil. How many cups of water? So we want to know what the relationship is between oil and cups of water. So we look up here and we see 1/4 cup of oil to 1/4 cup of water. Okay, now again, when we're looking at these ratios, we are assuming that our other ingredients don't run out. Okay, so that's what's going to be new on this. Okay, so we're going to have 1/4 cup of oil to 1/4 cup of water. Oil will cancel, 1/4 cup will cancel, and we know that we will need 1.5 cups of water. And we assume that we have enough mixes and we have enough eggs, just like up here. We assume we have enough oil and we have enough or excess water. Okay? How many mixes will I need if I have 1 cup of oil that I have to use up? Well, most of us don't cook this way, but you can think through the process. Okay? 1 cup of oil, mixes. You go back to the recipe and you ask yourself, what's the relationship? 1 mix to 1/4 cup of oil. Those are the relationships that give us the ratios, or what we call the conversion factors. And so we use our dimensional analysis to put the unit in the right place, like we've been doing all along. 1/4 cup of oil in the denominator to 1 mix. Cups of oil will cancel. When you divide by a fraction, you multiply by the reciprocal, and that says we have 4 mixes. And again, we are going to assume, if we're looking at oil to mixes, that we have plenty of eggs and we have plenty of water. Okay? So, again, this should be a review. Okay, if this is not a review, again, I will tell you to pause, go to the ancillary, go to the book, if that works for you to do that. What we want to do is do that in something that is less familiar, and that is the chemical equation. And so for most of you, this should be a review or something that you're just going to need to practice. Okay, so you're going to have, for example, this type of reaction. So what I might ask you is I might ask you reaction type, in which you would say this is combustion. Then I might ask you, is it balanced? And you would look at it and say, okay, yeah, that's balanced. I might ask you what the mole ratios are. And so you could tell me, for example, 1 mole CH4 to 2 moles of O2, etc., etc. Now, one interpretation is to talk about this in terms of molecules. 1 molecule of CH4 plus 2 molecules of O2 will yield 1 molecule of CO2 plus 2 molecules of water. However, if we multiply this up by 6.02 times 10 to the 23rd, then instead of molecules, this becomes a mole. So we're going to look at that in the next segment.